Am I audible?
Okay, sir.
So optical rotatory dispersion. So take a screenshot and go to the next slide. So it's the introduction first of all. So see some topics or terms. Plane polarized light. So introduction of ORT. See first term. Plane polarized light. So what is a plane polarized light? Plane polarized light. So then, when a ordinary light traveling in all directions, then when a ordinary light traveling in all directions, traveling in all directions is passed through a nickel prism. Is passed through a nickel prism is called is passed through a nickel prism. Nickel prism. So it travels only in one direction. So when an ordinary light traveling in all direction is passed through a nickel prism, it travels only in one direction. It travels only in one direction. Only one direction is called plane polarized light. So what is a plane polarized light? What is plane polarized light? It is a light or it is a source of light. So when an ordinary light traveling in all directions, when ordinary light traveling in all direction and it is passed through a nickel prism. So it is passed through a nickel prism. It is a nickel prism. So it travels only in one direction. So when the ordinary light traveling in all directions is passed through a nickel prism, so it travels only one direction. So that direction is called or is known as plane polarized light. Plane polarized light. Clear? Definition of plane polarized light. You may respond. Yeah. Okay. So next, so take a screenshot. So next, circularly polarized light. Circularly polarized light. Circularly polarized light. So what is a polarized light? So when an ordinary light is traveling in all direction is passed through a nickel prism, so it travels in only one direction. That is called a plain polarized light, right? The next term, circularly polarized light. So see the definition of circularly polarized light. So when a plain polarized light, when a plain polarized light is passed through a specially cut glass prism. Specially cut glass prism. So it is called as a Fresnel ROM. Fresnel's ROM. It is a specially designed prism. So when a plain polarized light is passed through a Fresnel ROM, so it travels in circular fashion. Circular fashion, which is called circularly polarized light. Circularly polarized light. Clear? So when a plain polarized light is passed through a specially cut glass prism, that is called as a Fresnel's ROM. So when a plain polarized light is passed through a Fresnel's ROM, so it travels in circular fashion, so which is called circularly polarized light. So see, so this is a source of light. So it is a passed through a prism or nickel prism. So it travels in only one direction. It is called plain polarized light. Plain polarized light. So when a plain polarized light, so this plain polarized light passes through a specially cut glass prism. Specially cut glass prism. So it is a prism actually. So it is a specially cut glass prism. So it travels in circular fashions. Circular fashion. So which is called as circularly polarized light. Clear? So this circularly polarized light consists of two components. So one is the right circularly polarized light. This is the right circularly polarized light. And second one, left circularly polarized light. Polarized light. So this right circularly polarized light is denotes with ER, and left circularly polarized light denotes with EL. So this is about a circularly polarized light. So what is a circularly polarized light? So when a plane polarized light is passes through a specially cut glass prism, so it travels in circular fashion. The light travels in circular fashions, which is called circularly polarized light. So what is a plane polarized light? So here, when a plane polarized light is passed through a specially cut glass prism. So what is a plane polarized light? When a light is passes through a prism, it travels in only one direction. It's called plane polarized light. It is a plane polarized light, right? So when the light in all directions passing through a nickel prism, so it travels in only one direction. It's called plane polarized light. So definition of plane polarized light. And next, see the definition of circularly polarized light. So when a plane polarized light passes through a specially cut glass prism, that is a Fresnel's round. So it travels in circular fashion, which is called circularly polarized light. So these circularly polarized lights consists of two components. So first one is ER, that is a right circularly polarized light, and second one EL, left circularly polarized light. So see the next page. So E, circularly polarized light, E equal to ER. What is ER? Right circularly polarized light, plus EL, left circularly polarized light. Therefore, E equal to ER plus EL. Take a screenshot. Is it clear? Circularly polarized light. So E equal to what? ER plus EL. So see. Next. So when a ray of polarized light, when a ray of polarized light consisting two components, that is a right circularly polarized light and left circularly polarized light, consisting of two components. One is a right circularly polarized light light, that is ER, and left circularly polarized component, EL. So listen, so when a ray of polarized light consists of two components, one is the right circularly polarized component ER and left circularly polarized component EL, is passed through a symmetric medium. Is passed through a symmetric medium. So the two components are transmitted with equal velocity. Symmetric medium. So then the two components are transmitted with equal velocity. So listen. So therefore, there is no rotation of plane polarized light. Therefore, there is no rotation. There is no rotation of plane polarized light. So listen. So when a ray of polarized light is consists of two components. So one is ER, that is circularly polarized light component ER, and next left circularly polarized light component EL. So these two components, right circularly polarized light component ER and left circularly polarized component EL, is passed through a symmetric medium. Is passed through both ER light and EL light passes through a symmetric medium. So the two components are transmitted with the equal velocity. The two components ER and EL are transmitted with equal velocity. Therefore, there is no rotation of plane polarized light. Therefore, in symmetric medium, the combination of ER and EL to give in the same plane. The combination of ER and EL to give in the same plane. Therefore, there is no net rotation of the plane polarized light. That means the molecule said to be optically inactive. So the net polarized light, the net rotation, no net rotation means optically inactive. Clear? So when you listen once again, so when the array of polarized light consists of two components, right? So one is ER, that is a right circular polarized light, and second one EL, left circularly polarized light. So these two components passes through symmetric medium. These two components passes through a symmetric medium. So these two components are transmitted with equal velocity. Equal velocity. So show the diagram. Show in diagram. Suppose so here this is X. So X is the plane of the polarized light. Plane of the polarized light. So here the two components, that is one is ER and EL, passes through a symmetric medium. So these two components are transmitted with equal velocity. They are transmitted through a equal velocity. ER and EL. It is E. So here equal velocity means here ER equal to EL in symmetric medium. So here theta equal to 0. There is no rotation. And theta equal to 0. Therefore, optically inactive. No net rotation. So here theta equal to 0. That means here optically inactive. Clear? So this is the two components are passing through a symmetric medium. And the two components ER and EL transmitted with equal velocity. Suppose in case of those two components passes through a asymmetric medium. So write down. Suppose So when a ray of a polarized light passes through a asymmetric medium, so then the transmission of ER and EL will be the different. So in symmetric medium, ER equal to EL, right? So in case of asymmetric medium, the rates of transmission of ER and EL will be the different. That is ER not equal to EL. ER not equal to EL. So write down here, ER not equal to EL. So write down. When a ray of plane polarized light consisting two components. So light circularly polarized light, that is ER, and light circularly polarized light EL through an asymmetric medium. So then the rates of transmission of ER and EL will be different. In asymmetric medium. So this phenomenon is called as circular birefringence. That is a CB. So when a ray of plane polarized light consisting two components, that is a right polarized light ER and left polarized light EL through an asymmetric medium. So then the rates of transmission of ER and EL will be the different. So in case of symmetric medium, they are transmitted with equal velocity. So in equal to EL. So in asymmetric medium, the rates of transmissions of ER and EL will be the different. That means ER not equal to EL. Suppose see the diagram. Circle. So X is the plane of the polarized light. So it is that the transmission of ER and EL will be the different. So here theta equal to some value E. So here theta. So that is equal to theta equal to positive. And ER not equal to EL. So this phenomenon is called as circular birefringence. See, circular polarized light. So when a plane polarized light is passes through a specially cut glass prism, so it travels in circular fashion. So which is called as circular polarized light. So this circular polarized light consists of two components. First one ER. That is a right circular polarized light, and second one is EL, left circular polarized light. So these two components, right circular polarized light and left circular polarized light, passes through a symmetric medium. Passes through a symmetric medium. So the two components are transmitted with equal velocity. So in symmetric medium, ER equal to EL. So here theta equal to 0. So optically inactive. So in the next case, so these two components ER and EL, right circularly polarized light and left circularly polarized light passed through an asymmetric medium. So here in this case, the rates of transmission of ER and EL will be different. That is the ER not equal to EL. So theta equal to some positive value. So this phenomenon is known as circular birefringence. Clear? So next, see circular birefringence. Circular birefringence. CB, circular birefringence, CB. So what is the circular birefringence? So we discussed in the previous topic. So here theta equal to some positive means is optically active. Therefore, optically active. So see the next circular birefringence. So definition of circular birefringence. See, so same. So when the plane polarized light is passed through an asymmetric medium. An asymmetric medium. So the rates of transmission of light. The rates of transmission of light circularly polarized light ER. Circularly polarized light ER, that is right, and left. So right circularly polarized light ER and left circularly polarized light EL. So the transmission of right circularly polarized light ER and left circularly polarized light EL will be different. So this phenomenon is called as circular birefringence. Circular birefringence. CP. So this is the definition of circular birefringence. So when the plane polarized light is passes through an asymmetric medium, the rates of transmission of right circularly polarized light ER and left circularly polarized light EL will be different. So this phenomenon is called as circular birefringence. Clear? Circular birefringence. CB. So this circular birefringence is responsible for the optical activity. So it is responsible for optical activity. Suppose, so I'm going to the next slide, take a screenshot. Suppose when ER travels faster than EL. So when ER, what is ER? Right circularly polarized light. When ER travels faster than EL, then the molecule said to be an dextrorotatory. Then the molecule is said to dextrorotatory. Dextrorotatory. And theta is positive. Theta is positive. So when ER, right circularly polarized light, travels faster than EL, then the molecule to dextrorotatory and theta is positive. Suppose when EL, left circularly polarized light, travels faster than ER, EL travels faster than ER, then the molecule said to be levorotatory. The molecule is said to be levorotatory. And theta is negative. This is about circular birefringence. So what is circular birefringence? When the plane polarized light is passed through an asymmetric medium, the rates of transmission of right circularly polarized light ER and left circularly polarized light EL will be different. That is called ER not equal to EL. So this phenomena is called as circular birefringence. Circular birefringence. So here, if ER travels faster than EL, then the molecule is said to be dextrorotatory and theta is fast. When EL travels faster than ER, what is EL? Left circularly polarized light travels faster than right circularly polarized light. So then the molecule is said to be levorotatory and theta is negative. So this is about circular birefringence. Clear? So take a screenshot and go to the next line. So next. Next, circular dichroism. Circular dichroism. CD. Circular dichroism. So see. So when two components of plane polarized light, when two components of plane polarized light, that is ER and EL. So when two components of plane polarized light, that is ER and EL, are absorbed by an asymmetric medium. And absorbed by asymmetric medium to unequal extents. To unequal extents. Unequal extents. The resultant light the resultant light E. The resultant light E will be elliptically polarized. Elliptically polarized. So this phenomenon circular dichroism. This phenomenon is called as circular dichroism. So circular dichroism, CD. What is circular dichroism? When two components of plane polarized light, so ER and EL, are absorbed by an asymmetric medium to unequal extents. Resultant light will be elliptically polarized. So this phenomenon is called as circular dichroism. Circular dichroism CD. So this is about CB and CD. Circular birefringence CB and circular dichroism CD. Clear? So take a screenshot. I'm going to the next slide.
Good morning, sir.
Good morning.
So once show the 1 to 5 slides, sir. I will take screenshot. I did not note, sir.
Which is the first slide? Plane polarized light.
Okay.
Screenshot.
Okay.
Second slide.
Okay, sir.
Third slide.
Okay, sir.
Fourth one.
Okay, thank you, sir. It's enough.
So next continuation. ORT curves. So what is ORT? What is ORT? Optically rotatory dispersion. We are studying about ORT. Discussing about ORT. Optically rotatory dispersion. So CB is completed. Next CD completed. Circular birefringence and circular dichroism. And next, see ORT curves. ORT curves. So, then ORT curves. So the variation of optical rotation of a compound with wavelength. With wavelength is called optical rotator dispersion. And the curves obtained are called and the curves operand are called ORT curves. This optical rotator dispersion curves. So see the variation of optical rotation of a compound with wavelength is called optical rotator dispersion ORD. And the curves often are called as ORD curves. So what are ORD curves? The variation of optical rotation of a compound with wavelength is called optical rotator dispersion. And the curves obtained are called ORD curves. So ORD curves may be two types. So two types. So first one, plain ORD curves. And second one, anomalous ORD curves. So these ORD curves are two types. First one, plain ORD curves and anomalous ORD curves. So first one, plain ORD curves. Plain ORD curves. See, plain ORD curves. So the curves do not exhibit a peak. So these curves do not exhibit a peak. Do not exhibit a trough. So these curves do not exhibit a peak or trough. So these are classified as two types, positive and negative curves, according to their tendency to become more positive or more negative decreasing wavelength. So plain curves, plain ORD curves do not exhibit a peak. And these curves are classified as two types, positive and negative ORD curve. So dependence to be negative, decreasing wavelength. Draw this diagram. So these plain ORD curves do not exhibit a peak. Negative ORD curves. So these are positive ORD curves. 0. So 220 nanometer. wavelength 700 minus this. So plus and minus plane verticals. Plus and minus verticals. So these curves do not exhibit a peak or troughs. So this is a zero rotatory axis. So these curves do not exhibit a peak, but they may cross zero rotatory axis. So this is a zero, and verticals minus verticals with decreasing wavelength. So these are plane ORD curves. So take a screenshot. And next, anomalous ORD curves. Second one. Anomalous ORD curves. So what are plane curves? So they do not exhibit peaks, called plane ORD curves. So here the anomalous curves have peaks. These curves are have peaks. Peaks are trough. And these curves are also known as cotton effect curves. These curves are also known as cotton effect curves. Cotton effect. And these curves also classify into positive and negative cotton effect curves. Depends upon the peak. So see the diagram. So these curves have peaks. It's optical reflection. Zero. So we have 220 nanometer. 700 nanometer. So these are the positive cotton effect curves. Positive curve, positive cotton effect curve, positive cotton effect curve. So see, negative cotton effect curves. Zero optical rotation and 220 nanometer, 700 nanometer. So these are negative cotton effect curves. These are negative cotton effect curves. Negative cotton effect curves. Say about anomalous ORT curves. So anomalous ORT curves have peaks. So these curves also known as cotton effect curves. These are positive cotton effect curves, and these are negative cotton effect curves. So what is the cotton effect? The combination of CB and CD is called as the cotton effect. Cotton effect. So these are ORT curves. So the variation of optical rotation of a compound with wavelength is called optical rotatory dispersion (ORT), and the curves obtained are called as ORT curves. First one, plain ORT curves, anomalous ORT curves. So what are plain ORT curves? So these curves do not exhibit a peak, and classified into positive and negative curves. These are positive and negative ORT curves. Positive and negative plain ORT curves. And second one, anomalous ORT curves. So these curves have peaks or troughs. So these curves also called as cotton effect curves. So these are positive cotton effect curves, and these are negative cotton effect curves. So see the what is cotton effect? See cotton effect, that is CE, cotton effect. So the combination of circular birefringence CB, the combination of circular birefringence CB and circular dichroism CD is called cotton effect. So the combination of circular birefringence CB and circular dichroism CD is called cotton effect. Therefore, CE equal to cotton effect equal to CB plus CD. Cotton effect equal to CB plus CD. Combination of circular birefringence and circular dichroism. Clear? Next continuation. Octane rule. So CB, circular birefringence, and circular dichroism, and cotton effect, and ORT curves. Completed. And next topic, octane rule and applications. So see, octane rule. Next, octane rule. Octane rule. So this it is an empirical rule. Octane rule is a empirical rule, and it was elaborated by Moffitt and Woodward and Moscovite scientists. Moffitt, Woodward, and mass pull in 1961. So here the rule permits the prediction of the sign of the Cotton effect. Permits the prediction of the sign of the Cotton effect for optically active cyclohexanones from their structure and configuration and conformation. So this Octane rule permits the prediction of the sign of the Cotton effect for the optically active cyclohexanones from their structure, configuration, and conformation. So see, so in Octane rule, the carbonyl group should occupy the head of the chair conformation or board conformation. So I will share one PDF. See here, Octane rule. So Octane rule. So it is an empirical rule, and it was elaborated by Moffitt, Hubbard, and Moscovitch, and Line and Desiree in 1961. So the rule permits the prediction of the sign of the Cotton effect for optically active cyclohexanones from their structure, configuration, and conformation. So to apply the rule, so see here first point, the carbonyl group should occupy the head of the chair or board conformation. So the carbonyl group should occupy head of the chair or board conformation. And the system is viewed along C double bond O bond. And next point, the cyclohexanone system is oriented in three-dimensional coordinated system. The cyclohexanone system is oriented in 3D, three-dimensional coordinated system. So these are 3D diagram of cyclohexanone. First you see observe the structure of cyclohexanone. So here C double bond group, C2 carbon, C3 carbon, C4, C5, C6. C1, C2, C3, C4, C5, C6. So here the three orthogonal planes divide the molecule into 8 octanes or 8 sectors. You have to see from your this side, this view. So here, first one. So three orthogonal planes divide the molecule into 8 octanes or 8 sectors. So first one, a vertical plane A So this is a vertical plane A. This is plane A. So don't confuse here. So this is a vertical plane A, passes through the carbonyl oxygen, that is C1, and C4. So here a vertical plane A passes through the carbonyl oxygen, that is C1 and C4. So both axial and equatorial bonds on C4 lie in this plane. So in C4, so both axial and equatorial bonds on C4 lie in this plane. That means in plane A. Here, say a vertical plane A passes through the carbonyl oxygen, that is C1 and C4. So both axial and equatorial bonds on C4 lies in this plane. That is plane A. And next, see a horizontal plane B. So where is B? It is B here. So this is a B plane, and it is passes through a carbonyl oxygen, and C2, C1, C2, and C6 also. So the plane, horizontal plane B, passes through the carbonyl oxygen C1 and C2 and C6. Here C2 here and C6. So equatorial bonds on C2 and C6 are almost in this plane. So here equatorial bonds on C2 and C6 are almost in this plane, that is plane B. Next, see another plane C. So this is a plane C. Another plane C. So it can bisect the carbonyl group. It can bisect the carbonyl group. So plane A passes through the carbonyl oxygen, that is a C1 and C4. Plane A passes through the C1 and C4. And both axial and equatorial bonds on C4 lie in this plane. Next, plane B, horizontal plane B, passes through the carbonyl oxygen and C2, C6. So here, equatorial bonds on C2 and C6 are almost in this plane. Next, another plane C bisect the carbonyl group. So see, here the 8 octanes are obtained, which are divided into 2 sets. So first one, 4 front are near octanes. Near octanes are 4 rear octanes are away from the observer. So these 8 octanes are obtained, which are divided into 2 sets. So what is set 1? Front. 4 front set or 4 rear set are 4 octanes. So first one, 4 front near to the observer, and second one, 4 rear octanes far away from the observer. So we have to take a screenshot of this page. Take a screenshot. So it is a 3D diagram. So here C1, C4. So plane A passes through a carbonyl oxygen, that is C1 and C4. And plane B passes through the C1, C2, C6. And another plane bisect the carbonyl. And these 8 octanes are divided into 2 sets. Set 1 is a front or near octanes or near sector. Second one, rear or far octanes are away from the observer. So take a screenshot. here. So the front 4 octanes are usually empty. Front 4 octanes are usually empty. So therefore, maybe these front 4 octanes are ignored. So the front 4 octanes or sectors are usually empty. Therefore, maybe ignored. So front 4 octanes are ignored. And next second one, rear 4 octanes. Rear 4 octanes are designated as lower right, that is LR, lower left, that is LL, and upper right U. UL. So rear 4 or back 4 octanes are designated as lower right LR, lower left LL, upper right UR, and upper left UL. And listen carefully, don't confuse here. So the back 4 octanes classify into lower right, lower left, upper right, upper left. So next, see one important point. So the substituents in upper left and lower right contribute towards positive Cardan effect. Positive Cardan effect. So upper left and lower right contribute the positive Cardan effect. Next point. And substituents in upper right and lower left LL contributes towards negative Cardan effect. So upper right and lower left contributes towards negative Cardan effect. Negative Cardan effect. So see here, 3D diagram. Suppose I'm writing here. C2, C double combo, C6. It's a cyclohexane molecule, axial, equatorial, equatorial, axial, and equatorial, axial, equatorial, axial. This is a cyclohexanone molecule. So see, these are by 60 carbonyl group. So here, so this is a upper right C3, upper right UR, and this is what upper left C5 UL, and C2 lower right, and this is left side, right? Next C6, lower left. Don't confuse here. So according to this line, so these are right side, left side, and upside, downside. That is the upper side, lower side. Don't confuse. So here, the upper right contributes which sign? Here, the substance in upper left, lower left, so lower right contributes positive cotton effect, and the substance in upper right and the lower left contributes negative cotton effect. So your upper right contributes negative cotton effect, and lower left, so upper left, here this is upper left, so upper left contributes positive cotton effect, and lower left negative cotton effect, and lower right positive cotton effect. So this is the structure of a cyclohexanone molecule. Don't confuse here. And this is a C1 carbonyl group, C2, C3, C4, C5, C6. So it can bisect the one plane bisect this carbonyl group. That is C11 group. One is the right side and another side left side. And here upper side, lower side. So this C3 is the upper right, C5 is the upper left, and C2 becomes lower right, C6 becomes lower left. So according to Octane rule, the substance in upper left and lower left are positive, contribute the positive cotton effect. So upper left, lower right are contribute the positive cotton effect. And the substance in upper right and lower left, contributes the negative cotton effect. Next. So take a screenshot. Next. So your C3, C6. First one, the substance in C3 and C. And next, the substance in C2 and C5. C2, the substance at C2 and C5. That is the upper left and lower right. Before the next, the substance in C2 and C5 contributes the positive cotton effect. This is about Octane rule. See here. So this is cyclohexane diagram. So the substance in C2 and C5. So upper left and lower left. So according to Octane rule, the substance in upper left and lower right contributes the positive cotton effect, and the substance in upper right and lower left contribute the negative cotton effect. So this is about Octane Rule. So is there any doubt in Octane Rule? It's about Octane Rule. So in the next class, I will explain applications of Octane Rule and alpha halo ketone rule, axial alpha halo ketone rule. So today we discussed about circular birefringence, circular dichroism, cotton effect, verticals, and octane rule. These topics are completed. So in the next class, I will explain octane rule, applications of octane rule, and axial alpha halo ketone rule. So is there any doubt in today's class? Is there any doubt in today's class? So listen. So optical rotatory dispersion, ORD. Listen one second. So plane polarized light. So what is plane polarized light? So when the ordinary light travel in all directions, it passes through a nickel prism and it travels in only one direction. So it travels in only one direction. It's called plane polarized light. So when the ordinary light traveling in all directions and is passed through a nickel prism. So it travels in only one direction. That is called plane polarized light. And next, circularly polarized light. Here, so when this plane polarized light is passes through a specially cut glass prism, and it is called as a Fresnel's wrong. So when a plane polarized light is passes through a Fresnel's wrong, so it travels in circular prism, which is called circularly polarized light. And these circularly polarized lights consists of two components. First one is a right circularly polarized light, that is ER, and left circularly polarized light, EL. So therefore here E equal to circularly polarized light equal to ER plus EL. So here these two, right circularly polarized light and left circularly polarized lights, again passes through a symmetric medium. So when the area of polarized light consists of two components, that is the right circularly polarized light ER and left circularly polarized light EL, is passes through a symmetric medium. So the two components are transmitted with equal velocity. So there is no rotation of plane polarized light, equal velocity. So here no rotation of plane polarized light. That is the net rotation is 0. That is theta equal to 0. That means optically inactive. So in this case, in the symmetric medium, ER equal to EL in symmetric medium. In case of this same ER and EL, right circularly polarized light and left circularly polarized light passes through a asymmetric medium. Passes through an asymmetric medium. So then the rates of transmission of ER and EL will be different in asymmetric medium. That is ER not equal to EL. So this phenomenon is called as circular birefringence. So here ER not equal to EL. That means here some theta equal to positive, some value. Therefore, optically active. They are optically active. So next, see circular birefringence, CB. So what is circular birefringence? So when the plane polarized light is passes through an asymmetric medium, so the rates of transmission of right circularly polarized light ER and left circularly polarized light EF will be different. So this phenomenon is known as or called as circular birefringence. Just 2 minutes, sir. I will finish within 2 minutes only. And next, CD. So when two components of the plane polarized light, ER and EN, are observed by asymmetric medium to unequal extents, so the resultant light E will be elliptically polarized. So this phenomenon is called as circular dichroism. Circular dichroism. So next, see what decouples and octane rule. So this is enough for today, and remaining the next class. Bye. Or you can start the meeting, sir. You can.